This is the interface of GreenEYE, where the remote sensing with pure image processing is displayed. And as you can see, as I go down, there's a lot of information on this page with the implementation pictures of all orthography. So when I click Sense Now, it redirects to a login page where you can either log in with your Google account or your email and password. So in this case, I'm just going to go with the Google. So once you press the Google button, it will redirect you to the main dashboard, where this is the dashboard that will be profiled for the user after they log out. There is 3 options for the user. First up is the crop counting, second is the crop matching, and the third one is the logout. So when the user click on crop counting, it will redirect the user to another page where they have 4 types of algorithms to count their crops. So in this case, we're going to use a papaya orthography. So this is the image. So we're going to count how many crops is in this image. Algorithm, which is the binary noise removal for crop counting. So it has a 49% accuracy of ground truth accuracy. So the user interface is very simple, where the user can just click on this choose file button and just choose the image. In this case, I'm going to choose the image, and then just click the submit button. But once the image is processed, you can get to see the binary denoise version of the papaya image with the threshold graph of binary values. And then here you can see how many crops is there overall. And when you click on this image, you can actually see in detail what is the image is showing. So let's move on to the next algorithm, which is the canny edge detector. So canny edge detector has even low accuracy with only 24%, test with the same image. So display the CMAP, dilated CMAP, and also the RGB contour overlay. So in this case, this algorithm detected that there is 303 crops. This has relatively low accuracy compared to the binary noise removal before. Next up is mean shift without HSV. So this is a very poor algorithm where it has only 8% accuracy. So let's test the same image. See, the image has been mean shifted over here to make it smooth. Results in 842 crops out. So the last one is mean shift with HSV. So this one has a 95% accuracy. 3 steps this algorithm to be used. So first up, you need to perform mean shift watersheding using the HSV picker, where we can actually download the HSV picker using this link. So if you click this link, you'll be redirected to a Google Drive page where you can download this HSV picker. It is a software kit where you can just download and play in your PC. So you downloaded the HSV picker. So when you click the HSV picker, this is the interface of it. So just click select an image. It will bring you to the selection menu where we're going to select the same papaya image, and then it's going to display you the interface of HSV picker, where here we need to do a small process to separate the foreground and the background. Once we are done with the HSV picker, what the HSV picker does, it will send the value to the Firebase icon over here, where the lower HSV limit and the upper HSV limit will be uploaded here. And then when we choose the file over here and then click submit, what the system will do, it will accept the values from the Firebase to be used as the HSV upper and lower limit in order to do the identification. So as you can see, this is watersheded plus mean shifted output, where the accuracy is very high. Out of 72 crops, it detected 70 crops over here. So this is a very high accuracy algorithm among all the other algorithms that was used. Next up is the crop matching. So if you go to the crop matching over here, first up is the template matching, where in order to find the single label in a whole ortho, so let's upload a whole orthography image. So that we're going to use the same image, and as the single label, we're going to use this image, where this represents one of the crop from the whole ortho. And then we're going to submit this, and then the system is going to find out where is the crop in the whole ortho, and then it's going to give us a bright green spot over here. So if I zoomed it out, you can see a bright green spot over here. So this is where the single image is located. Okay, you might ask, why is this important? This is important for the user or for the farmer to upload any kind of single label of a tree and then compare it with the whole orthography of their farm in order to identify the anomaly between the crops, or to identify the crop with problems in their whole ortho in a very easy manner, rather than just going there and physically and finding out where is the crop located. So that is for crop matching in crop anomaly detection. Next one is the crop anomaly capture, where we can use the same image again and then display analysis in 5 different attributes. So in this case, this is the analysis of this image, where if we hover here, it will show you the area, eccentricity, perimeter, and the intensity mean of each areas over here. So this is important in the case to identify the differences between the crops that is located in a farmer's farm. So what does this represent in this analysis? Alright, so if you see this whole image, this whole part is conquered by one color, which is orange. So this is the biggest part in this area. So what does this mean? This whole area or if you see here, this area represents of the image consists of equivalent size or equivalent attributes of trees, and this area covers this area where it has equal size of attributes of trees. So this enables the farmer to get to know more about their crops rather than just blindly farming. So these data will be used further in order to identify the soil quality in these certain areas. So why does this have this characteristic at this area? So maybe the soil has high strength, or this part is equivalent, or maybe the soil has low strength or low quality or whatsoever. So these data can be used further for more in detail analysis. So that sums up our GreenEYE in a whole. This project is just a starting point for remote sensing because mostly we are using UAV footages. Further upgradation, this project is planned to be deployed using satellite images and also Landsat images, and also Sentinel data from Google Earth Engine. As a business proposal, this crop counting algorithm has 4 of the accuracy over here. So we can pick the highest accuracy and put a subscription to it so that the user can pay in order to use the service. So that sums up this whole system. Thank you so much for watching. I hope this project brings a starting point for remote sensing.